Right. Good. Okay, so another thing is, John, I mean, do you prefer that people interrupt you, have questions?
Yeah, sure. I mean,
right. So
it's easier.
All right, cool. So yeah, just interrupt him as he goes along. So with that, John, please, you can start.
So thanks a lot to the organizers. I've been following some of the sessions so far in this nice series. So hopefully I won't bring down the standard too much. These are obviously sort of unprecedented times to have an Irishman speaking on St. Patrick's Day, and not a single pint of Guinness to be found on the island of Ireland for 2 consecutive years running. So yeah. So look, I mean, I returned to Ireland about about 2 or 3 years ago, to Trinity College Dublin, and actually started a reasonably large size group. But this was actually the last time we managed to take a group photograph together. So this picture was taken in 2019 in a lecture room, which is called the Schrödinger lecture room. It's where Schrödinger gave these famous lectures, What is Life? So if you ever visit in 3D, hopefully I can take you and show you around. It's quite nice. And as you all know, this is very much the mode of doing theoretical physics in the last 2 years. So look, before I begin, I just want to tell you about some of the topics that we study in the group, because I mean, I'm not entirely familiar with the community I'm speaking to, but I'd say we have sort of 3 main interests at the moment. The first interest is more on the sort of quantum information side, so thinking about sort of near scale quantum information processing devices, and I'm particularly interested in the sort of thermodynamics of such devices. So what is entropy production on an NISQ device? Is there a fundamental link between information processing and thermodynamics, like we know, for example, in the case of Landau erasure? And because these systems are often very far away from the thermodynamic limit, they're very prone to fluctuations. And the other topic that, of course, we study a lot is sort of how does thermodynamics look in this type of intermediate sort of size systems where fluctuations are extremely important. So that's the idea of sort of lifting concepts from stochastic thermodynamics over to situations where you have sort of quantum coherence, etc., in the energy eigenbasis. And sort of the topic that I'm going to talk about today is probably the topic that connects most with the audience that I'm speaking to, which is thermalization and transport in complex systems. So often we're very interested in steady state transport. So when you have a kind of complex system which is not necessarily integrable and is connected to bats that drive currents, and we're interested in issues such as the emergence of thermodynamics and the emergence of sort of standard stuff that you expect. So what I'll talk about today is a sort of hodgepodge or a mixed bag of a bunch of results that we've got over the last couple of years with various different people. So the main collaboration is between myself, my student Marlon Brennis, Marcus Rigol, which I'm sure you all know, and also some very close collaborators from my previous days in Trieste, Alessandro Silva and Silvia Papalardi, who recently moved to ENS in Paris, and more recently we've been working a bit on Mark Mitchison on topics connected that I'm not really going to have time to talk about. So the first thing I'm going to do is I'm just going to outline what models that we're studying. This is very much a talk about numerics by the nature of the things we're interested in here, and then tell you about some sort of curious high temperature ballistic transport calculations which we've performed, and then show you how this connects with the well-known topic of eigenstate thermalization, and I'll tell you about some ongoing work. So that's going to be the sort of structure of the talk. I mean, the real hero of the story is Marlon, who's really a numerical expert, and he's been performing many of these calculations because they involve either sort of DMRG calculations or large-scale exact diagonalization. He's been performing those simulations on K, which is the supercomputer in the national supercomputing facility called iCheck. So I just want to give a bit of a shout out to them for their support. All right, so what we're going to start off with is a very sort of familiar situation of when you take an integrable model, and for the purpose of this talk, that integrable model is going to be the XXC spin chain, and we're going to break integrability in two different ways. The first way we're going to break integrability of the model is by introducing a spin defect in the center of the chain. So it's known that such a situation is enough actually to break integrability in the sense of level spacing statistics, like I'm going to show you in a second. And then we're going to also study, in contrast, an integrability breaking term, which is sort of extensive. It spans the sort of size of the system. So that's going to be a staggered field where you have a sort of field on every second site. Okay, so basically perturbations of the XXC chain. So as you all know, I don't have to really spend much time in it. The XXC spin chain is non-trivial, but yet integrable. And if you do a kind of analysis of the spectrum, you find a Poissonian level spacing distribution, okay, which is a hallmark of integrability. And this goes back to the older works of Berry and Tabor. So if you take this model now and you perturb it in one of those two ways that I've just described, you find that the level spacing statistics changes from Poissonian to Wigner-Dyson. So you see the onset of level repulsion, and that's, you know, again consistent with the notion that the spectral statistics of chaotic systems should have this famous sort of distribution. It often surprises people sometimes, but it's by now well accepted that even an infinitesimal perturbation, you know, in the center of the chain is enough to sort of to break the integrability of the model. It's of course in finite size systems difficult to see it. You have to go to reasonably large field strengths, but it's well known, and it goes back to older works by Lea Santos and Zotos, and more recently by the Paul Kovnikov group. I saw a seminar in this series discussing a similar sort of model. Okay, so what I'm actually interested in now is the situation of high temperature transport in these models. And I'm going to start in a sort of, let's say, slightly unconventional way of thinking about transport, and that's from an open systems perspective. So what I'm going to consider is something called boundary driving. So boundary driving is sort of open systems approach to transport. So what you have essentially is you have dissipation which acts on the boundaries. Okay, so this term is a dissipative term, and it acts on the left and the right. And so what do these dissipators do essentially is they impose a magnetization imbalance across the chain. Okay, so the jump operators for the experts, and it's a Lindblad master equation. The jump operators are basically sigma plus and sigma minus at the boundaries. And what this does is essentially it generates, a non-homogeneous, or can generate a non-homogeneous magnetization profile, and hence a current. I should point out as well that for the experts is that this is not really a microscopically consistent, thermodynamically consistent master equation, in the sense that you can only really consider this as replicating high temperature transport, because it's not like the standard thermodynamic master equation where you include a real spectral density in the bath. So for example, if you wanted to replicate sort of transport calculations that are done with non-equilibrium Green's functions or whatever. So it accurately reproduces the high temperature transport in linear response, but you can't really deal with anything outside of that sort of infinite temperature regime. Nevertheless, I mean, we're working on other ways of extending this type of an open system scenario with tensor networks. This was the topic of this paper, where we were focusing really on thermodynamics of, albeit quite small systems. But in the paper, you can show that we can also do sort of spin chains like XXC, etc., at finite temperatures for both energy and spin transport in finite temperatures. So it's not a new story. There's plenty of other groups have thought of such a scheme as this, but what I would say is that the tensor network scheme that we apply to solve the dynamics is quite nice, and it seems to work quite well. So I mean, I should really say that I'm not going to spend any time to discuss how you actually perform the numerics. I mean, but just to let you know, it's that what you do essentially is you exploit the fact that the dissipator is local, and then you can do exactly the same tricks as you do with standard time evolution with DMRG, namely trotterization, write it as an MPO, and away you go. The other thing which maybe is not familiar is that actually this technique, counterintuitively to say doing closed system dynamics with DMRG, is that it works better for ergodic systems. I mean, so you basically run the thing for a long time, try to reach a non-equilibrium steady state, but I'll explain that now. Okay, so what you want to do is you want to try to extract a non-equilibrium steady state. So this means taking a kind of long time limit. So you allow these dissipators act on the boundary. And what happens is that you get a magnetization flux in the bulk. So this defines a current operator. So if you think about the derivative of the expectation value of, say, a local magnetization on the bulk, then you can write this in terms of the difference of a current operator just by continuity. And by virtue of the fact that if you take the long time limit, and this is a true non-equilibrium steady state, then what you can see is that the derivative of the expectation value of the magnetization is equal to 0. And this means essentially you get a homogeneous current profile across the bulk, okay? And now the idea is that you want to study how this current scales as a function of the chain length in that non-equilibrium steady state and try to tease out the transport properties. So that's the scenario that we're considering. So just to recap on the scaling theory in case it's unfamiliar to people. So, I mean, the basic idea of transport is usually you take some sort of inhomogeneity and you allow it to evolve in your many-body system. And roughly speaking, you look at the variance of this local inhomogeneity and it grows as t to the power of 2 alpha. So when alpha is equal to 1, that would be a diffusive like behavior, whereas, you know, anything in between then would be anomalous. So from the perspective of looking at currents and steady states, okay, you can also sort of look at how what type of transport property you have by scaling the current in the non-equilibrium steady state. So the current goes like 1 over L to the nu, and these exponents are related by this phenomenological like construction. You can see it's fleshed out the argument in a classical paper here by Li and Wang, but just to show you what you expect. So if you have diffusion in your many-body system, the current's going to scale like 1 over L, okay? And that would mean essentially that Fick's law would apply locally on the chain. So you would get a sort of gradient in the magnetization profile. Likewise, if you have ballistic transport, then the current would not scale with L, and kind of, well, I don't really like this, but some people say that it's like the diffusion coefficient scaling like the system size, okay? But the key point is that the current will not scale as you increase the system size when you have ballistic transport. And anomalous diffusion occurs essentially when you have something in between. For example, if you have subdiffusion, then the diffusion coefficient scales like L to the power of 1 minus nu, with nu being greater than 1. And you can see that that means that any finite L, you can define a diffusion coefficient, but that diffusion coefficient goes to 0 in the thermodynamic limit, okay? And the opposite is true then for superdiffusion. And of course, localization is when the current decreases exponentially with the length with some exponent, which is the localization length. So that's how the scaling theory of transport works. So before we move on to the models that I just explained, let's look at some, you know, very well-known calculations that have been done in the literature. So this technique of boundary driving was basically, I would say, the first people to apply it to tease out high temperature transport properties of spin chains were the Ljubljana group, in particular Thomas Prosen and Marcos Niederich. And of course, there's a very long literature in how the scaling of various currents in these systems behaves in the high temperature limit. So if you look in, for example, the gapless phase, so when delta is less than 1, and you perform a very large sort of dynamical simulation here. So people often wonder, how can you get to such large system sizes? And the trick is, of course, with boundary driving, that the non-equilibrium steady state is actually a matrix product operator with a very low bond dimension when you have certain features. It's not always the case, but in this case of the XXC, it certainly is. So what you can see here, if you run this type of simulation, is you see that the current is becoming independent of L, signifying the well-known ballistic character in the gapless phase, okay, at high temperatures. And so now the other way of seeing this sort of ballistic transport is that if you look in time, so you do a time evolution with your dissipator in this scheme, okay, and you look at the profile of the magnetization across the chain, ballistic transport in the long time limit would mean essentially that you would have a flat profile in the bulk. Okay, this is the signature of another way of seeing ballistic transport. This was actually the very first calculation the student Marlon did to benchmark the numerical code that he generated. So this is for about 80 spins, and you can see this ballistic plot. So everything is looking okay. If you take the staggered magnetic field, and a staggered magnetic field is a global integrability breaking term, and what you do if you look at this magnetization profile across the bulk, well, you see what you might expect. You see that the magnetization profile across the chain develops a slope, and that's a signature of diffusion, okay? So this slope is a signature of diffusion. And indeed, if you scale the current as a function of system size, you find a nice almost 1/L scaling. It's like 0.98. It can be improved with slightly larger system sizes for the purpose of illustration. So again, I mean, this non-integrable model gives over to diffusion in the thermodynamic limit. So there's diffusive hydrodynamics. I mean, you can see it very clearly from scaling as a function of L in this setup, okay? I should point out that this type of calculation is quite hard to do by means of exact diagonalization because you're limited in terms of the system size for this type of model for obvious reasons. And also any sort of TDMRG scheme in this is also extremely difficult because you can't evolve for a very long time, but this is the advantage of this technique. So let's move on to the single impurity case. So in the single impurity case, what you see is you see what you might expect, which is you put that impurity in the center of the chain, and what starts to build is a kind of domain wall structure in the non-equilibrium steady state. So you see positive magnetization starts to build up to the left of the impurity and negative to the right. And in the limit of taking H going to infinity, you literally cut the chain in two, okay? So how about transport? And that's kind of the next thing. So how about the scaling of the current, right? So if you look at the scaling of the current here, you find that the current is completely ballistic. So it's independent of L, at least it appears at up to 100 system sizes of 100 or so, and we've increased that system size slightly since. So what you see here is the current as a function of the system size for various different impurity strengths, right? So what you see, first of all, is the expectation that the current should decrease because you're creating a constriction, but you don't really see a significant change in the scaling behavior, right? So if you want, it's a bit like the problem of having a single, it's a bit like the problem of having ballistic leads impinging on a single kind of barrier. And this is where I get this scaling for the current as a function of H by a very simple envelope calculation of assuming that situation. So that's quite interesting that the transport across the system remains ballistic and coherent because it has level spacing statistics which are Wigner-Dyson, and as far as I can kind of think, it is quite difficult. I don't know of any other example that has Wigner-Dyson level spacing statistics and completely coherent transport. But I mean, at the same time, level spacing statistics probe timescales on the system which are sort of going like the mean level spacing, whereas transport is something which occurs with with sort of much shorter timescales. I mean, it's still long, but short comparison to inverse level spacings. So we want to take this a little bit further. And it was kind of the first result that we had, and it confused us slightly because there was conflicting work in the literature. So in this paper, the authors studied exactly the same model. They studied again this issue of the level spacing statistics. And then actually they concluded by a calculation of this charge stiffness. So this responds to a sort of flux going through the chain with periodic boundary conditions. Because this was going to zero, then they concluded that you had incoherent transport, which seemed at odds with the result that we got from boundary driving. And actually, that's where Marcus Regol comes into the picture. So I was in Santa Barbara in the summer of 2018, and he was on sabbatical, and I was telling him about this issue, and that was confusing us. So, I mean, he pointed out the following issue. So the idea now is that we were going to look at this from a more traditional approach. So looking at the kind of current correlation functions and really thinking about the conductivity in a Kubo sense. And obviously, the signature of ballistic transport is the presence of a peak at zero frequency, the so-called Drude weight, right? But it was Marcus actually who pointed out the following subtlety, okay, which is that even if you have periodic boundary conditions, as soon as you introduce an impurity on the chain, you break translational symmetry. And then what you can do is actually you can define a current operator in a different way, because a position operator on the chain emerges due to this breaking of the translational symmetry. And you can define the Drude weight, or the current operator from the Drude weight, from the sort of basically from the one way of writing down the Drude weight is the diagonal matrix elements, but these of course are zero. So actually, as he pointed out to me, which is an old work by him and Shastri, is that the Drude weight is not a meaningful thermodynamic quantity if you break translational symmetry. And what you have to do instead is you actually have to look at the entire frequency distribution of the conductivity. Okay, so you really should look at how this thing scales, the entire correlation function as a function of frequency. So what you see here in the first box, forget about the inset for now, is open boundary conditions. So translational symmetry is broken in the clean XXZ, no impurity. And we're just doing a kind of ED calculation. But what you see here is these are system sizes. You can see that the spectral weight, okay, in the function is moving towards zero in the thermodynamic limit. And you see exactly the same in the situation with the single impurity. So it is consistent with coherent transport if you look at the entire frequency distribution of the object. So what you can do is you can take this sort of area, property normalized with a sum rule, and you can see where it's going in the thermodynamic limit. And indeed, what you see, this is for the single impurity case, is that if you do a finite size scaling, it indeed looks like that you have the weight going towards zero frequency. This is consistent with ballistic transport. So that was sort of Marcus's input in the initial project to tell us that, look, it's very subtle when you break translational symmetry. But anyway, just to summarize so far, what I've been saying is that a single impurity breaks the integrability XXC in the sense of level spacing. Its transport properties are similar to the clean model, and both the steady state kind of picture of transport, the non-equilibrium steady state picture of transport, and the Kubo-like theory can be made consistent with each other if you're careful. And the conclusion is basically that you have no diffusive hydrodynamics in the case of single impurity, okay? And we confirmed this for both cases. So a big question for us then was, how about thermalization, okay? So typically you expect systems which are not integrable to thermalize in the sense that you all know about. And this issue of thermalization, well, I have these slides in there because I often speak to a different audience, but nevertheless, if you take an integrable system, which has an extensive set of conserved quantities, then we know from these famous experiments that the system will not thermalize to a microcanonical distribution, but rather to a generalized Gibbs ensemble, which is essentially the state when you maximize the entropy functional subject to the constraints. So you can do all sorts of nice things experimentally now with cold atoms. For example, you can tune between kind of integrability and non-integrability, and you can see the onset of thermalization. This is, for example, in this dipolars Newton cradle experiment where you have a sort of tunable interaction by means of a magnetic field. But the paradigm is this, right? So what do I mean when I say thermalization here? Of course, it's thermalization in an isolated system case. So I'm taking some isolated system, okay, it has some spectrum, and I'm starting with some initial state, which is a superposition of the energy eigenstates. So these guys are just the overlaps with the initial state. And all you kind of require is that this state would have extensive energy. So it's scaling like n, with sub-extensive energy fluctuations would scale like 1 over n, right? And so the distribution kind of is it's smooth and it's peaked around the average energy with these fluctuations which are subextensive. And so what do I mean? Well, I mean, imagine I do a quench, okay, and I allow the system to evolve, then you get basically a, you know, sort of spreading of information and conserved quantities in the model, etc. And if I look at a generic local observable, you're going to get behavior whereby the observable sort of evolves in time about some average value. And that average value is, of course, the time average, so the so-called expectation value of that observable in the diagonal ensemble. And that would be true, you know, generically, whether your system is integrable or not. But I mean, the big question is, of course, is when generically can I safely replace the expectation value in the diagonal ensemble with the expectation value in the microcanonical one? So when does this happen generically? That's the issue of thermalization in isolated systems. So, I mean, the standard explanation is the eigenstate thermalization hypothesis, which was sort of introduced by Mark Trinity back in the 90s, building on previous work by Berry and others. And he's sort of made an ansatz for when this should be the case. So there's a lot of information in this ansatz, and often, you know, it's studied in the sense of diagonal elements, but as this talk will show, I mean, the off-diagonal matrix elements are, of course, the ones that are important for transport. So, I mean, you have two energy scales here. You have an E bar, which is an average energy, okay, something like this here. You have frequency difference, omega. And he said, look, you know, you get thermalization when your system becomes a smooth function of the energy, and your off-diagonal matrix elements decay with a term which is exponential in the entropy. So this is going like 1 over root the density of states, so exponentially small in the system size. But also you get this smooth function, which basically will, as we'll talk about later, will encode the correlation functions, the 2-point correlation functions. And then you have this random variable, okay, which is zero mean and unit variance. So that's the sort of ETH ansatz in all its glory. And every single term in it is really important. We're going to go through them in detail in the models that I just explained, okay? So, I mean, how does it work? So if you think about what the diagonal ensemble is, well, you get this type of a situation where, you know, it's like Cn squared, which are the overlaps with the initial state of the energy eigenbasis. And what you do now is you make an expansion of the diagonal matrix elements about the average energy. And okay, if you do it carefully, this term goes away because of the smoothness property. And what you're left with is that the time average is equal to this function of the smooth function of the energy plus some term in the fluctuations. I'm kind of going fast here because I expect that everybody here knows this stuff, but I had to learn it. So, I mean, essentially what you see is that, look, the diagonal prediction, if the ETH holds, is going to give you the same expectation value as in the microcanonical ensemble up to some sub-extensive correction in the fluctuations, okay? So that's sort of the diagonal matrix elements. Now, the other thing you need to show, of course, is that the actual time evolution of your observable should remain close to that time average value for most times. And you can make a very simple argument based on the fact that the off-diagonal matrix elements are exponentially small in the system size, and that's enough to sort of bound this fluctuating term, okay? So that's how you make that argument. And the last thing is, well, what about the sort of structure that's in the off-diagonal matrix elements? And that's going to be very important for what I want to talk about next, okay? So how do I sort of interpret these? Well, this is all connected to the sort of 2-point correlation functions of the model. So for instance, if you write down a connected correlation function on an eigenstate, okay, what you do if you do it carefully, you can see it very well done in the review by Delesio, Polkovnikov, Regal, etc., is that you can see that you can express things like the symmetric response function and the Kubo response function up to sub-extensive corrections, basically in terms of this mod of f squared, which is the smooth function in the off-diagonal of the ETH, okay? So it's quite beautiful, actually, when you think about it, that the ETH is much stronger than saying that observables relaxed, they're microcanonical, but you also require that the fluctuation dissipation theorem actually holds as well. And you can show that that's all true up to sub-extensive corrections. Okay, so if you can extract mod f squared, then you can also study transport, two-point correlation functions of general observables, etc. All of the usual stuff that condensed matter physicists love. Okay. So how do you extract this this stuff? Okay, well, what you can do is you can look at the off-diagonal matrix elements, okay, the mod squared of these things. So if you define the kind of variance, okay, and what you can think about doing is doing a kind of coarse graining in frequency bins, right? So what you're going to do is you're looking within a given sort of frequency window, you compute the variance, and then you move the window through the spectrum, and what you'll extract up to this prefactor, which you can also work out, is going to be mod f squared, okay? You can extract mod f squared up to an energy-dependent prefactor. So you just do full ED, and you're careful with your sorting, etc. So I'm going to show you how all of these things look now in the two models that I explained in the talk, in the start of the talk, okay? So let's do the experiments, the numerical experiments, and let's focus on the staggered field model, and let's do a very large ED. So this model has U1 symmetry. It has a couple of other symmetries that we break by hand, but we resolve the U1 because it helps us numerically. And we go up to kind of n is equal to 20 system sizes. So if you look at a generic observable, here I'm choosing sort of, it's a 2-point observable, but it doesn't really matter. And you look at a scatter plot of the diagonal matrix elements as a function of the energy density, what you see is that as a function of the system size, okay, these matrix elements are forming a smooth line as predicted by the ETH, okay? Furthermore, if you look at the eigenstate to eigenstate fluctuations, these are expected to basically decay as something exponential in L, or 1 over square root d, where d is the Hilbert space dimension that occurs very nicely in the staggered field model. So it completely fulfills the ETH in the sense of the diagonal matrix elements. And actually, you can show that the agreement between, say, if you take a local observable and you look at the expectation value in an eigenstate, which are the red dots, which is the sort of idea of the fluctuations becoming very small, that this is fully consistent with sort of matching it with the canonical prediction up to sort of reasonably low temperatures. Low temperatures starts to break down at the edges of the spectrum, etc. So that's the staggered field model. And how about the off diagonals? So this comes from another paper that I'm not going to discuss, okay? But I mean, a paper of ours, basically. But let me just explain here, these red dots, if you want gajillions of them, these are essentially the off diagonal matrix elements. And the black line now, this is a semi-log plot, okay? The black line is mod f squared for the operator, which is sigma z, okay, in the staggered field model. And what you can see in the semi-log plot, well, the only thing you can really see is that you see that it falls off exponentially with the frequency, okay? And that's pretty generic behavior. You can also look at the susceptibility, the response functions, and what I do here is I show comparisons between the susceptibility for the spin-spin correlation function, okay, with the corresponding canonical prediction. And you can see that you get beautiful agreement in terms of the correlation functions, right? So as you'd expect. So ETH is holding very nicely at the level of both the diagonal and off-diagonal matrix elements, okay? So you can extract these correlation functions very nicely. I mean, in this paper, we actually use this model to prove something else related to Fisher information that I don't want to discuss, but I'm happy to discuss it with you after the talk, but I want to move on. So what happens in this case of the single impurity is probably the most interesting thing. And what you can see here now is two different observables that we choose. One is an extensive observable, the kinetic energy, and one is the on-site kinetic energy away from the impurity site. And what you see is quite nicely is that this small impurity is enough to make basically the system fully compliant at the level of ETH. So a single impurity is enough to thermalize the model. Okay, so I think this is very illustrative if you compare this with what would happen if you analyze the matrix elements of just the clean XXC, okay? Well, if you analyze the matrix elements of the clean XXC, because it's integrable, of course, it doesn't fulfill ETH. So what you see is that this thing is not becoming a smooth function of the energy, so as you'd expect. However, you see something quite remarkable here, right? You see that the microcanonical prediction of thermodynamics, which is the black line, is equivalent in both models. So if you want, the single impurity is irrelevant on, it's forcing the system to thermalize in an ETH sense, but in the sense of thermodynamics, it's completely irrelevant. It's thermalizing the system to the microcanonical prediction of the clean XXC. Okay, so that's a very interesting result. We found it particularly nice that a single impurity is sufficient to do that. And the question is now, what about the off-diagonal matrix elements in the single impurity model? And this is where this interesting sort of transport that is predicted to be ballistic should show up.
So, do you mind if I ask a question at this point?
Of course.
Can you go a slide back? Right. So, so also the local, the bottom quantity satisfies ETH in this sense.
I mean, okay. So in this on the right hand side is this. So panel B and D is a single impurity model. And,
that's correct. Yeah.
And this is fully consistent with ETH. Okay, you can see that the diagonal matrix elements are becoming a smooth function of the energy. You see that the eigenstate to eigenstate fluctuations are behaving as they should. On the other hand, if we compare with just the matrix elements of the integrable XXC, it is not fulfilling the ETH. You can see that the support of the distribution is remaining finite as you increase the system size. Okay. However, as I was saying, what's curious is that, and makes sense if you think about it, is that the single impurity, it breaks the integrability of the model, but still you thermalize to the microcanonical prediction of the clean XXC.
I guess that bit is indeed not surprising, but it is surprising that it makes you thermalize to that value, even for the lower operator. Somehow for the top, it's less surprising, I thought.
Yeah, I mean,
okay, yeah, no, sorry, I just wanted to make sure I read correctly this slide.
Sure, I mean, I guess this is the first result. The first thing is that single impurity is enough to thermalize a model, and it thermalizes to the microcanonical prediction of the clean model, okay? And it also shows you how fragile integrability is in general. If I put one defect there, I mean, it sort of, you know, it thermalizes the system. Of course, this says nothing about timescales, right? But this is another story. I mean, okay, so I want to get to the off-diagonal matrix elements because I think this is where this sort of story it gets even more interesting. Okay, if I do this procedure, so this is in a work by Marilyn, Marcus, myself, kind of last year, is if you look at this single impurity model, it's perfectly consistent with ETH at the level of the off-diagonal matrix elements as well. You can see you get a bunch of them. You can extract what you see here. This black line is this coarse graining procedure, which gives you mod f squared from ETH, okay? And what you see is that, well, you know, you get, again, the standard exponential cut off, the semi-log plot, I should say. Sorry, I've cut off the y-axis. You can see it in a second. But if you compare, and this is something that Marcus is very interested in, which is if you actually do this for the integrable model, okay, for different observables, is that you can also extract information on the correlation function, okay? And you can see again that they're very similar, the integrable and the non-integrable model. In fact, in the bottom panel, I show in the insets the standard sort of plot, okay? And you can see that what you can extract there at lower frequencies is precisely the same kind of correlation function in frequency space that I extracted in the first part of the talk, right? So it's fully consistent with doing it the other way with the Kubo formalism. Okay, you just get it here from matrix elements. So that begs the question, right? I mean, is that it seems that there's not particularly that much difference between the integrable system and the integrable system which is perturbed with this integrability breaking perturbation in the sense of off-diagonal matrix elements, okay? And so what would be the signature here of of breaking integrability in the sense of off-diagonal matrix elements. And actually this is quite nice, is if you analyze now the statistics, yeah, of the matrix elements within these sort of frequency windows, right? So it seems that, you know, what does the ETH require? It actually makes no requirement on the form of the distribution that these things should follow. Often people say it's Gaussian because it has a unit variance and zero mean, but it's not necessarily required. You can still compute correlation functions if that's not the case, okay? So, I mean, it turns out that as soon as you turn on this small perturbation, this is a Gaussianity indicator. So if you divide, you know, the sort of average squared by the squared average by the average squared, if you have normal statistics, this is an indicator, it will be pi over 2. And what you can see is if you do this sort of calculation to analyze the frequency dependent statistics here, is that the XXZ model has highly non-Gaussian statistics, right? Still has a log normal distribution is what Marcus found, okay? But it's a remarkably sensitive indicator of integrability breaking, right? So you see, if I look at just the Smoothen quantities, if I look at the matrix, it's very difficult to see. But if you look at the statistics themselves, they're spectacularly sensitive to integrability breaking, more sensitive than I've seen before. And other people are sort of studying these things as well at the moment, right? So I want to talk a little bit about the statistics. So, I mean, it's Gaussian, right? But there's no particular reason for it to be Gaussian per se, because when you compute the correlation functions to get transport, etc., all you need is the property of a unit variance and zero mean. But of course, you could find another distribution that's funny, which has those properties, and it still works, okay? So we were trying to figure out what this actually means. We still are not completely sure, but let me point something else out, is that we did analysis recently at, you know, all of this work in the previous few slides was done at the sort of infinite temperature. Okay, so fixing a E bar at the center of the spectrum. But actually, you can see that this Gaussianity, when you break integrability, is a sort of signature right down to fairly low temperatures. I mean, obviously not down to the spectral edge where ETH wouldn't apply anyway, but it seems to be very, very sensitive, you know, kind of to the integrability breaking as a function of the temperature. And we explored this in this recent work. Now, you might ask yourself, okay, I mean, okay, fine. How about the statistics between, you know, matrix elements? Is this sort of IID stuff? And of course it cannot be. I mean, this was a very nice work recently, which also studied this model of the single impurity by Jonas Richter, Robin Steinweg, Joachim Gemmer, Anatoly Darmatsky. And what they actually did was quite interesting. They said, okay, obviously, if you look, you know, at if you look at the matrix elements, you know, in a given sort of kind of frequency interval, yeah, I mean, it cannot be IID, yeah, because I mean, obviously, the observable, if it's a local observable, will imprint this sort of two-pronged distribution because of the nature of the fact that it's a Pauli operator, right? Nevertheless, if you start to restrict your statistical analysis to a banded matrix by kind of defining a frequency cutoff, you can always sort of find a frequency range if you keep restricting your statistical window down low, at which the statistics of the operator look GOE, so look like a random matrix, right? And that's very interesting. And I mean, okay, it's certainly something which is observable dependent. Okay, it's not a generic property. It's observable and model dependent. I've noticed that ourselves. Okay, but why is it important, this thing? Well, of course, what you need, what the ETH doesn't describe is higher than 2-point functions, right? So, for example, let's suppose, for argument's sake, that really the ETH was, you know, sort of IID Gaussian random variables. Well, then, you know, you wouldn't get all of this stuff of growth of OTOC, etc., because you could trivially break up your higher order correlation function into a kind of product of 2-point functions, right? So those correlations between frequencies need to be there in order for you to get sort of stuff going on for higher order correlation functions. You wouldn't expect something like a Wick theorem to hold in a strongly interacting many-body system. But what we did in this recent work here, so this sort of idea that, that ETH, doesn't sort of describe these sort of higher order correlation functions, but you can get bounds from it, was in a paper by Trinity quite recently, and by Kershan and Fahini, which describe the reason for these correlations to be there. But in this work that I just want to mention, I'm not going to talk about it in any detail because I'm almost ready to be quiet now, is basically what we did is we played devil's advocate here. And I just want to explain the result and we can talk about it afterwards, is let's assume that the matrix elements, were IID in ETH, that they were statistically identically distributed, right? Then you could get an expression for the square norm commutator. And what we did was we started to analyze in time the behavior of this sort of result where you impose ETH uncorrelated and you basically compare it against an ab initio sort of full dynamical simulation of OTOC. And what you can actually use it for is you can see that this sort of frequency scale at which the matrix elements become uncorrelated, right, corresponds, the inverse of that frequency scale corresponds to a time scale at which the OTOC saturates, right? So whereby after which your operator dynamics or your correlation function dynamics is describable by random matrix theory. Now, the interesting thing is that people often ask, is this the Thouless energy or the Thouless time? And in my opinion, it's not. I mean, this random matrix time scale, from what we've seen, now we need to do proper finite size scaling, which we weren't able to do, but it seems highly observable dependent and system dependent, whereas the Thouless time would be something which would depend on the diffusion coefficient, right? So, I mean, here you see something which is really operator dependent. So our idea was just to exploit this sort of, at what point you become uncorrelated in frequency, looking at the matrix elements, this corresponds to some time scale for random matrix theory to emerge. So that's basically all that I have to tell you. The conclusions are, I mean, this local impurity, it's enough to destroy spectral signatures of integrability in the sense of level spacing statistics, but it has ballistic transport. And I think the important lesson there is that spectral statistics kind of probe timescales at the level of the inverse sort of mean level spacing, whereas ballistic transport and stuff like that is something which scales polynomially in the system size rather than exponential. Okay. There's a lot of information in those off-diagonal matrix elements that kind of help you round up the picture. And the result was that the single impurity, a single speck of dirt, is sufficient to thermalize the system to the microcanonical prediction of the clean model. And it also inherits the transport properties because, I mean, it's still an infinitesimal perturbation, so it's not thermodynamically relevant, I would say. Nevertheless, I mean, it's important dynamically, right? So the Gaussian statistics of matrix elements are a highly robust and sensitive indicator of integrability breaking, probably as sensitive as anything that I've seen. Correlations between matrix elements control higher order correlation functions, which are not describable within the ETH ansatz. And at the moment with Mark Mitchison, we're currently doing a project which is connected to this by considering BATs for open systems, which are ETH states, and trying to do sort of thermodynamics without ensembles at the level of open systems theory. So with that, I'd like to say thanks, happy to discuss, happy St. Patrick's Day.
All right, thank you, John. Are there any questions?
So I had a question. So what would happen if this impurity is not strictly local, but maybe it has some exponential?
Yeah. So okay, I don't have a plot to show you, but I can take the question. So actually, Marko Snidrich within boundary driving has studied a very similar scenario to what you're actually describing. So basically, he starts to study transport on a chain where he systematically puts a dopant density. Okay, So I mean, this is very different to say, for instance, disorder, really just like growing, increasing the density of impurities. And what you would see is that the region, the impurity region, becomes progressively more diffusive. So, I mean, let me show you something that I didn't have time to put into the talk, because it's also true. I told a bit of a white lie. If you look away from the impurity, yeah, I mean, the microcanonical prediction of the clean model and the XXE completely agree. But at the impurity site, you will see diffusive scaling in the analysis. I can show you the plot. It makes sense when you see it. So. Diffusion is just at the impurity site, but when you average over the magnetization over the whole chain, it disappears. Let me show you the plot. It makes a lot of sense. I think I included it in the somewhere in the back. Yeah. I mean, so look, I mean, this is now at the impurity site. Okay. This is, you see now that the microcanonical prediction is not the same, but this is unique point. This is the expectation value of sigma z at the impurity site in both the clean and perturbed model. So in all other instances, the microcanonical predictions would be the same except at the impurity site, and we see diffusive scaling here. And you can see then if you look at a global quantity, it washes it away by average that again, the microcanonical predictions are the same.
All right. Does anybody else have any questions? I mean, I have a fairly naive one. So is it going to also be the case that for a single impurity for a system that is just free fermionic, if you have a single sort of term breaking that nature in the middle, would you also get the same type of behavior in the sense that you get thermalization to the?
No. So we studied it. You don't get thermalization. It will not agree with the ETH in that case, but it will still just have ballistic transport. That's for sure. In the XX model with an impurity, but you would not see any diffusive scaling now at the actual impurity site, because I think the role of interactions is to create dissipation at the impurity site. So
when you say you put an impurity though in the XX case, is that impurity? What type of impurity?
Just a magnetic defect. So really just sigma z on that central site, which is different from the sigma z's on the rest of the chain.
Yeah, but that doesn't break.
It won't break the. I mean, it won't break the integrability of the free chain. I mean,
but that's what I was asking. If I do break the integrability by adding, I don't know, some other term,
like interactions,
like an interacting term. Yes, right. Do you know what?
Yeah, I mean, there you will expect ETH to be there if the impurity is there, right? But
so in the same manner that sort of locally it looks like it's ballistic, but nevertheless the whole sort of the scaling of the ETH type scatter plot would.
Yeah, I mean, this single impurity thing is quite interesting to me because it really shows you some nice things. It shows you how fragile integrability is. First of all, because it really takes very little to break that.
Well, I mean, I was thinking more, because for the XX case, for the XX case, I mean, you're breaking integrability, but also translational invariance by doing that. And I was thinking, is it that? Yeah, no, but I mean,
as soon as you introduce an impurity, even in the clean case, I mean, you'll in the non-interacting case, I mean, you'll break, even if you have periodic boundary conditions, you break translational symmetry anyway.
Right, but that's not enough. Okay, yeah.
Oh.
Cool. Thanks. That was it.
Yeah. No,
good. Does anybody have any hopefully deeper questions than mine? Because I was almost ashamed to ask this question, but, since nobody was saying anything.
Sorry, I have a question. Thanks for the talk. So I guess your model with the impurity in the middle of it reminds me of some kind of like many-body sinized billiard. Where you have like a single particle in a rectangular box and you put the single billiard in the center. And I guess you have quite a good idea of how the matrix elements of the impurity perturbation look in the basis of the eigenstates of the integrable system.
Well, that's it.
Yeah, so I was wondering, like, if you can think about like timescales associated with some kind of diffusion of the system in the basis of the original eigenstates.
No, that's a good point. So I mean, so for instance, can you see this integrability breaking at the level of, if I choose as a basis the integrable model, right, and then I sort of represent everything in that basis? Yeah, I mean, I think you can probably see this hybridization occurring, right? So, but I haven't explored it. I mean, but it's a good point.
Okay, thanks. So like you can't yeah, and I was thinking if you could maybe guess some kind of L dependence of the, or I guess you've got N dependence of this diffusion time.
Oh, I see. Yeah, I mean, it's a good point. I never thought about it, but it seems plausible. I mean, thanks for the.
Are there actually any
Sorry,
impurity?
sorry, Zlatko, you broke up a little bit.
Are there any? Yeah, so I was just going to ask if there are any rigorous results about
So the only thing,
single
yeah.
impurity.
So the only thing that I know is that low energies of that model is a famous problem, right? Because it's a Lottinger liquid with an impurity, and it's this famous Kane-Fisher problem. And there, you know, depending on the sign of the interactions in the Lottinger liquid, you can get actually zero conductance, right? So, but it's connected to, I mean, there's a universal behavior as a function of temperature. It's something that I'd like to do. It's known how the conductance scales with temperature at low energies, but of course, you know, you're talking about the high energies in what I'm studying, but somehow being able to connect these two as a function of temperature would be very nice. So that's number one. Number two is I only know the recent work that Dre Sells talked about in this series about the AGP norm, but this is also numerical work where they studied precisely this type of model as well, with very low sort of impurity strength, and showed that this sort of AGP norm object is a very sensitive indicator of integrability breaking as well. But I mean, I didn't see any analytical, maybe they did some perturbation theory actually. I'm not sure. That's what I know. I mean, we actually started studying it by accident, I would say. I mean, we were really at the start of the PhD project just using it to benchmark some code, and it turned out then we worked on it for a few years because it was interesting. But that was the thing.
Okay, I have a question. So if I take a conventional non-integrable system, then the fluctuations of any local observable around the Gibbs ensemble value at late times will decay exponentially, right? What about the non-integrable system you have where you break integrability at one point? I'm asking this because you're talking about correlations between off-diagonal matrix elements, and that is what would encode the fluctuations. So
you mean the temporal fluctuations?
The temporal fluctuations, yes.
I mean, we didn't study them, but I mean, they're still bounded by virtue of the ETH holded, right? I mean, they're exponentially small in the system size, right? Because the ETH holds. But I mean, we didn't study that. I mean, it's just, you can just show if ETH holds, then this is true. But I didn't.
Yes, but I mean, my concern was that, as you said, ETH doesn't immediately tell you about the correlations between the off-diagonal matrix elements.
That's right. That's right.
So I can understand that if ETH holds, yes, that then at late enough times, my local observables would indeed thermalize. But the question was that would they thermalize exponentially? I mean, okay, so for instance, Zlatko is an expert on this. For instance, in MBL systems, you still do get equilibration, not thermalization, but equilibration, but the temporal behavior is a power law in time.
Yes.
And in conventional robotic systems, equilibration equal to thermalization is exponential in time. So is it something intermediate here?
Well, I mean, look, I mean, there's something that we still need to look at. I mean, which is a full time dependent simulation here. I mean, my impression of what should go on is that, you know, it's something like pre-thermalization plateau will happen where you put the single impurity there, you do some dynamical simulation, and there's some, you know, the system thinks it's integrable up to some L star, okay?
Right.
And then after L star, it starts to feel the perturbation and it thermalizes to the microcanonical prediction of the clean model. And that L star, okay, that plateau will scale like L. So you'd never see it in the boundary driving kind of calculation. You only ever see ballistic transport. But I mean, this is a conjecture. We haven't done this dynamical simulation.
And do you see any signatures of this in your in your correlation functions, in the frequency dependent
Yeah,
correlation functions?
yeah. So if you, I mean, okay, this is a good question. So if you scale, I mean, if you're away from the impurity site and you look at a correlation function away from the impurity site, you'll see that, you know, you'll get the data collapse as n omega, okay? And this would be a signature of sort of ballistic behavior. But if you look at the impurity site, you'll see n squared omega scaling, right? So n squared omega is diffusive scaling at the impurity. We have seen this. It's in a PRB. We plot these things and with the data collapse.
Okay.
Yeah.
Okay. Yeah. Thanks.
All right.
Achilles, are you still recording this? Because I mean, I would like to ask Zlatko a couple of things about scars, if possible. But
that's up to, I can stop it. In fact, I stopped it.